Example 16.2. In this example, we explore a common way to measure the thermal conductivity of a material, which is simply done by sandwiching an electrical thermofoil heater between two identical samples of a material. The thickness of the resistance heater, including its cover, which is usually made out of silicone rubber, it is usually less than 0.5 millimeters. A circulating fluid, such as tap water, keeps the exposed ends of the sample at a constant temperature. The lateral surface of each of the samples is well insulated to ensure that the heat transfer is only one-dimensional. Two thermocouples are embedded in each one of the samples at some distance L apart from each other, and a differential thermometer reads the temperature drop delta T across the distance along each one of the samples. When steady operating conditions are reached, the total rate of heat transfer through both of the samples becomes equal to the electrical power drawn by the heater. In this particular experiment, a cylindrical sample of 5 centimeters in diameter and a length of 10 centimeters is used. Two thermocouples in each sample are placed 3 centimeters apart. After initial transient conditions, the electrical heater is observed to draw 0.4 amps to 110 volts, and both differential thermometers read a temperature difference of 15 Celsius. Our goal is to determine the thermal conductivity of this particular sample. To start the problem, let's do a small schematic about what we're looking for. So basically, these are the two samples that we have, right? So we have two of them. And they basically, each one of them sandwiches this resistance that we have over here in the middle. So we have a certain resistance that goes through here, and that resistance creates an electrical power. Once we have reached steady conditions, the amount of electrical power gets divided to go half into the upper material, and the other half goes into the lower material. So basically we have half of it goes to the top and half of it goes to the bottom half. Okay, so what we want to do is we want to analyze either one of them, because at the end, since it's a steady state, each one of the values will be basically the same. So we could choose the top, let's see. So the first thing that we're going to find out is what is that value of that electrical power. The electrical power is the multiplication of the voltage times the current. In this case, we have a voltage of 110 volts and a current of 0.4 amps. If we multiply these two values, we get 44, and the final unit is going to be watts. Therefore, if we want to find out the amount of rate of heat transfer going through each one of the materials, is going to be half of the electrical power. That means that it's going to be equal to 22 watts. So we know from Fourier's law, since we have a one-dimensional conduction case, Fourier's law is going to be evaluated simply as K, A, the difference between temperatures, and the distance between the 2 points in which we take the measurements. So in this case, notice that we have the location of them. So there's going to be one thermocouple at one position, and then the other one at the other position. And they told us that the distance between them in this particular case is going to be 3 centimeters. They also told us that the value of the area, it's going to be the shape, it's going to be a circle, because it says that it's diameter. So the cross-sectional area is simply going to be pi over 4 d squared. Okay, so notice that in this case we have a 5 centimeters diameter. So pi over 4, make sure that you transfer this into meters. Therefore, the value of your area in this case is going to be 0.001963 meters squared. So now notice that we have all the values. We simply have to solve this equation to solve for the thermal conductivity. So the thermal conductivity is simply going to be the value of Q dot times L divided by A times delta T. So now let's substitute the values. So we have 22 watts. The distance is going to be 0.03 meters. The value of A is going to the area we calculated to be 0.001963 meters square. And the value of delta that they provide us was equal to 15 Celsius. So after we plug these values in, we get that the value of K is going to be equal to 22.4. And now notice the unit, so this cancels with this. And then it gives us simply watts, MK, M delta C. Or you could also write it as W, watts, MK. Notice that these two units are exactly the same, since when we use Fourier's law, we multiply by a delta, and once again the delta of a Kelvin is exactly the same as the delta of Celsius. So both of those equations, both of those units are perfectly correct. The other thing that you have to notice is that it doesn't matter whether you evaluate the top or the bottom. Once we have reached steady state conditions, the assumption is that the amount of heat going to the top and going to the bottom is the same. And since the distance between the thermocouples is exactly the same, the result should be the same.